Okay, so we got a question on the board that is kind of a Newton's second law, kind of a Newton's third law type of question. Okay, it's about using horses to drag two logs that are chained together. Okay, so there's a chain that connects them to the horses' harnesses, and there's a chain that connects the logs to each other. The first log is 150 kilograms, and the second log is 250 kilograms. Okay, and then we know some of the forces. So part A, fairly straightforward. You're calculating the acceleration of the logs. Okay. Part B is the one that's more the Newton's third law kind of question. All right, so we'll see what you remember here. Get your diagram drawn. Let's see how we do. So let's start out just looking at part A here. Okay, so we've got our team of horses. We have log A, which is 150 kilograms, and we have log B, which is 250 kilograms. All right. So we know the horses can pull with 2,600 newtons worth of friction, worth of applied force, and there are 2,400 newtons worth of friction on the entire system. So basically, we can simplify this to 400 kilograms being pulled this way by 2,600 and this way by 2,400. So basically, it's a very simple Newton's second law system question, okay, where our net force would be 200 newtons, and our acceleration would be 200 newtons divided by the mass of the system, 400 kilograms, which gives us 0.5 meters per second squared forward. Okay, that number is going to be important for part B. Okay, you're going to need the acceleration of the individual boxes in order to solve part B, or individual logs in this case. Can you solve this with either log? Part B. Okay, you can. And you can solve this with either log. Okay, either one will work. One of them will require you to do an extra subtraction operation. Nothing terribly difficult. All right, give you a few more minutes on that, but you definitely have to separate them if you were kind of lost. You got to pick a log, okay, and use that one to figure out the answer. All right, so as I was saying, you can pick either log to solve this problem with. A is a little bit quicker because there's one less operation to solve it with. Okay, so they tell us that the force of friction on log A is 900 newtons. If you pick the other log, you have to go 2,400 minus 900 to get the friction on that log. It's not a difficult calculation, but it's an extra calculation. Okay, so I'm going to start with log A. The 150 kilograms, there's 2,600 newtons pulling forwards on it. There's 900 newtons worth of friction here. And what's the other force on log A?
The force of tension.
Yeah, the tension in the chain that's connecting the two logs, which is what the question wants me to find. Okay, what can I calculate about that log right now?
Acceleration.
Actually, I already have the acceleration. What can I use the acceleration to get? Fnet, yeah. Okay, so I'm going to go Fnet equals m times a, because I calculated the acceleration in the first part. So I'm just going to take that 150 and multiply by 0.5, and that's going to give me 75 newtons forward. All right, so I just did m times a. What do I usually do after that? Sum of all forces, yeah, okay, because if I'm going to find T, I now know 2 out of the 3 forces and what they add up to, so I can find the one I don't have, right? I just have to say that F net equals that tension plus the force of friction plus the applied force from the horses, okay, and then just isolate T. So that'll be F net, which I calculated to be 75, minus negative 900, okay, because friction is backwards, minus the applied force of the horses, 2,600 newtons, okay, that will give me the tension in the chain, which for this is going to end up being negative just because it's a backward force from the first log's point of view. Alright, so does that come up to 1.625, I think? Or sorry, 1,625? Right, 1,625 newtons. Okay, but there's only 3 significant digits, so 1.63 times 10 to the 3 newtons, and I don't have to put any direction on there because it was tension. Okay, had they asked what's the force of log B on log A, then I would have to say backwards. All right? Oh, sorry, they do ask for that. So backwards would be the right answer. Sorry, I thought we were looking for tension. Okay, so backwards. Okay, to solve that with the other log, really not all that different. Okay, I just have a 250 kilogram log. This is the force I'm looking for. It's the tension in the chain. And then I've got, it was 900 and 2400, right? So, is that right? No, I did something wrong there. That doesn't seem right. Nope, that's right, 1500 newtons. Okay, so I'm going to take my 750 or 250 kilograms here, multiply by 0.5, okay, and that will give me my net force, okay, and my net force will be 125 newtons. Okay, and then I can take that and subtract the 1500, which will leave me, or actually this will be negative 1500, which will give me exactly the same number, 1,625 newtons. Okay, but now it'll be forwards, okay, because it's from log A, or from the log B perspective. All right. Questions on that one? Pretty typical Newton's third law question. Okay. All right. Okay, this is a super easy Newton's third law question. All right, give it a try. There's no like log A and log B. It's just two people and they just do this. Okay. They just push off. And then we're going to look at an everybody jumps situation. Like we talked about the other day when everyone tried to reverse the spin of the Earth or start the Earth spinning or whatever by running, which was stupid. Okay, in order to solve this question, what do I need to know, or what do I need to understand?
Surface is frictionless.
Okay, surface is frictionless. What else? They push against each other. What's the nature of the forces? Yeah, well, they're not just the same net force, but I mean, kind of, yeah, same net force because there's only that one force. The force acting on each person is the same because of Newton's third law. Okay, when they push on each other, okay, when one pushes on one, the other one pushes back with the same amount of force. Only one person actually has to push here, okay, because the other person will automatically push back, okay, just because of Newton's third law. So, since I know the mass of student A and the acceleration of student A, I can find the force, which I can then apply to student B because the force has to be the same on them, except instead of east, it'll be west. Okay, so I just do 38 times 0.6, right? So if I want to get that force, okay, it's just mass times acceleration, 38 times 0.6. 22.8. What is it? 22.8 newtons. And okay, and then I just say, all right, I want to find the mass of student B. So I take that force, 22.8, and I divide it by the acceleration of student B, which was 0.75, and when I do that, I get that they are 30 kilograms. Okay, everybody all right with that? Okay. So there's not a lot to that question, but I do have to understand that every action has an equal and opposite reaction if I'm going to solve it. Okay, let's have a look at something a little bit different here. Maybe a little satirical even. I think that's the right word. Okay, so we were talking about this the other day. If everybody runs, we can reverse the spin of the Earth. If everybody jumps, we'll knock it out of orbit. Okay, things like that. So, start of the scenario, and the entire population of Earth is magically transported to one place because, well, quite frankly, that's the only way we would get them all there. Okay, it would have to be magic to move 7.5 billion people, okay, into one place all at the same time. It would be a nightmare. A person like me, just, yeah, I'd freak out, man. Okay, so everybody's there. And this crowd would take up an area the size of Rhode Island, which is the smallest state in the continental United States. Okay? So there's no reason to use a vague phrase like an area the size of Rhode Island. Let's just say we're doing this in Rhode Island, in the state of Rhode Island. And everybody on Earth is there, shoulder to shoulder, packed in like sardines. Okay? So we now have all these people, and they take up the entire state of Rhode Island. Okay? At the stroke of noon, everybody jumps. Everybody. Because everybody on Earth can jump. But we gotta pretend. Okay? What's that?
Oh, yeah, it is. It's going to totally be trash.
Okay, so this isn't going to affect the planet very much. Earth's mass is enormous. Okay? Earth's mass is 5.98 times 10 to the 24 kilograms. Okay? It's big. It's very, very big. Okay? So, Earth outweighs us by a factor of over 10 trillion. And I mean us, I mean all the people on Earth. Okay? It still outweighs us by over 10 trillion times. All right? So, on average, we humans can vertically jump maybe a half a meter on a good day. We're just going to say that's an average, that everybody jumps a half a meter. Because obviously there's like super athletic people who can jump a whole meter or more, and then there's people with a credit card vertical, okay, who would struggle to jump over a credit card laying flat on the floor. Okay, so that's what we got. All right, so we're going to say everybody jumps half a meter. Everyone jumps and falls back to the ground. Now, with that push, the Earth would be moved less than an atom's width. Okay, very, very small amount. All right, so technically though, everyone returning to Earth from a height of 1 meter would deliver a fair amount of energy. You'd be able to hear the rumbling sound like thunder, okay, of everyone landing back on the Earth. In fact, you'd probably even feel it if you were there. Okay, feel that kind of tremor or whatever, okay, running through the Earth. Okay? It'd be no small amount of energy. The slight pulse of pressure spreads out through the North American continental crust and dissipates with little effect. The sound of all those feet creates a long, drawn-out roar which lasts many seconds. The air grows quiet. Seconds pass. Everyone looks around, wonders what the point of it was. Okay? There's a lot of uncomfortable glances. Someone coughs, which, post-COVID, that'd be a big deal. Okay? Because you got everybody in the whole world in one place, and yeah. Okay. So, a cell phone comes out of a pocket. Within seconds, the rest of the world's 5 billion phones follow. Okay? All of them, even those compatible with the region's towers, are displaying some version of no signal because the cell networks have collapsed under the unprecedented load. Because that would happen. Okay? Outside Rhode Island, abandoned machinery begins grinding to a halt. Okay? There are a lot of things on Earth that are quite dangerous and require constant supervision. Nuclear power plants would come to mind. Okay? But where is everybody? Jumping. This is going to end badly. Not because we knocked the Earth out of orbit, but it's just going to end really badly. Okay? So, the airport, okay, in Warwick, Rhode Island, handles a few thousand passengers a day. It's kind of like the Red Deer Airport. Okay? Like, it's not big. Okay? Assuming they got things organized, including sending out scouting missions to retrieve fuel, they could run at 500% capacity for years and make no dent in the crowd of 7 billion people. Okay, so the addition of all the nearby airports doesn't change the equation very much. Neither does the region's light rail system, so like the sea train. Okay, we pack a lot of people in the sea train and run it constantly. Okay, crowds climb on board container ships. Well, we all know how well that ends. Okay, when like you know, they're trying to smuggle people from one place to another in container ships, it very often ends very badly, okay? So in all the deep water ports in Providence and places like that, but stocking sufficient food and water, not to mention the sewage problem, okay, proves to be a bit of an issue, okay? Rhode Island's 500,000 cars are commandeered. Moments later, the biggest traffic jam in the history of humanity occurs, okay? So most cars are engulfed by the crowds, kind of like The Walking Dead, right? Like they're just everywhere, okay? And a few lucky few get out and begin wandering the abandoned road network. Some make it past New York or Boston before running out of fuel. Since the electricity is probably not on at this point, rather than finding a working gas pump, it's easier to just abandon a car and steal another. Because, well, where are the police? Jumping. Okay, so yeah, you could do that. Okay, so the edge of the crowd spreads outward into southern Massachusetts and Connecticut. Any two people who meet are unlikely to have a language in common, and almost nobody knows the area because, well, they can't just Google it. The cell network collapsed already. Okay, so the state becomes a patchwork chaos of coalescing and collapsing social hierarchies. Walking Dead. Okay. Violence is common, everyone is hungry and thirsty, grocery stores are emptied, fresh water is hard to come by, and there's no efficient system for distributing it. Nobody has mentioned the sewage problem, okay, but it's going to be a problem. Human waste is disgusting and going to cause disease, and nobody has mentioned that, okay. Within weeks, Rhode Island is a graveyard of billions. This didn't work out very well, because we magically transported everybody there. But we couldn't magically transport them all away. You only use the magic once. All right, so the survivors spread out across the face of the world and struggle to build a new civilization atop the pristine ruins of the old. Our species staggers on, but our population has been greatly reduced. Okay? Earth's orbit is completely unaffected. It spins along exactly as it did before our species-wide jump, but at least now we know. Okay, so let's have a look at some questions here to do with this thing. So what are some problems with the synchronization of everybody's jump? We just said at the stroke of noon, everybody jumps. Does your watch read the same as mine? Half of you don't even wear a watch anymore, you just use your phone. Okay? It might not. Okay, I mean, if you're using your phone, everybody's clock is going to be close to the same because they synchronize with the cell network. But remember, the cell network was down. So how do I get a crowd that stretches basically from like almost one side of the province to, well, not that far, but let's say from Lethbridge to Edmonton, okay? How am I gonna synchronize a crowd that big? I'm not. Yeah, I got no chance of that. Sound travels at 333 meters per second. It's not like I can just fire a gun and hope that everyone will hear it and jump at the same time. Okay? For one thing, it's not, the sound's just not going to travel that far. And secondly, by the time it reached the edge of the crowd, if I was in the center, it'd be like an hour later. Okay? This is not going to work. Okay? So I don't know how you synchronize that and get everybody to actually jump at the same time. Okay? Let's calculate the total mass of Earth's population, assuming the average mass of a person is 65 kilograms. Okay? So if I want to do that, I'm going to take we'll just say 7 billion people for the sake of expediency here. So, yeah, that's 7 billion. All right, there's the mass of the entire human population. Is it a lot smaller than the mass of the Earth? Yeah, absolutely. Okay, 4.55 times 10 to the 11th. Kilograms. Okay, calculate the total gravitational potential energy of the crowd when they're at the maximum height of their jump. I don't know if you remember this from Science 10, but we calculate gravitational potential energy by going m times g times h. Okay, mass times the acceleration due to gravity times the height. All right, so everyone was falling from a height of 0.5 meter. This is our mass, and obviously g is 9.81. All right, so we're going to take our 4.5, we're going to take that number there, multiply by 9.81, and then multiply by 0.5 meter. All right, so there is the amount of energy that the entire human race can put into the Earth by jumping 0.5 meter. Okay, it's a lot, 2.23 times 10 to the 12 joules. Okay. Determine the kinetic energy of the crowd as they strike the earth after their fall. So that's their potential energy when they're half a meter off the ground. According to the law of conservation of energy, how much energy do they have when they come back to the ground? That number, right, so that's easy. Okay, we don't even have to do anything. We just have to understand that conservation of energy says it'd be the same. Okay, so the law of conservation of energy says that energy cannot be created or destroyed, but the kinetic energy of the earth would be less than that of the crowd. Explain this difference. Okay, when everybody lands on the ground, the earth's not perfectly rigid. Okay, so what does some of that energy do? Yeah, bends the crust, people leave footprints, that's what we say, bending across footprints, divots or whatever. Okay, the sound, right, we said it would make a big sound, sound's a form of energy, so that represents some of that energy not doing work on the earth. Okay, but we'll just say for sake of simplicity, it was all conserved and it all did work on the earth. Okay, so, we want to determine the maximum kinetic energy of the earth as a result of the crowd hitting it. So last year in Science 10, you learned that kinetic energy is 1/2 times mass times speed squared. Okay? Now, the amount of kinetic energy the earth would receive would be this much. Everyone okay with that? Right? Because that's the amount of energy the crowd had, so it has to be transferred to the earth when they land. All right? So we want to calculate the maximum speed of the earth as a result of the crowd hitting it. So I want to solve for v. I know this number because it's right there, and I know the mass of the earth because I wrote it up there before, 5.98 times 10 to the 24. So if I manipulate this equation for v, it will be the square root of, okay, that 2.23 times 10 to the 12 divided by 1/2 of the Earth's mass times 5.98 times 10 to the 24. All right, so let's punch that in. So that number divided by, in brackets, 0.5 times 5.98 e24. And then I'll square root that number. There's the speed of the earth imparted to it as a result of the crowd hitting it. 8.6 times 10 to the -7 meters per second. So that's what was the number? 8? 8.6 or something like that. Meters per second. Is that going to knock the Earth out of orbit? I think not. All right, so would there be any noticeable effect? No. Okay. There's stuff that hits the Earth that would do a lot more than that. Okay, Earth gets hit by meteorites that would do more work than that. Okay, and it doesn't knock Earth out of orbit. For now, because we get hit by a really big one, then we might be in trouble.
If that did happen and you got that acceleration, would that eventually go away or would it keep accelerating the Earth at that speed?
No, the acceleration only lasts as long as the force is being applied. So for that instant. So that's the speed it would produce, which is nothing. The Earth would completely absorb that. The moon does more to the Earth than that every day, pulling it back and forth, wobbling, moving the ocean for the tides. It does way more than that every single day. So no, that's going to do absolutely nothing.
If we jump from way higher, would there be any noticeable difference?
Not really. I mean, it would kill everyone.
Yeah.
Yeah.
And if we all fell out of the sky?
Yeah, it still wouldn't do anything. Sure, we'd have more energy, but only linearly so, right? Because it's not, the height's a linear relationship with energy. So there's really nothing that we could do. Like, when we set off a nuclear weapon, it would do more, right? Not that anyone hopefully will do that, but it would have more energy than that. So it's not going to, there's really nothing we can do to knock Earth out of its orbit, thankfully, because there's people out there, I guess, who might think about it. But okay, yeah, pretty straightforward. So it's ridiculous. That's why that whole running to reverse the spin of the Earth thing was ridiculous. Okay, mass of the Earth, huge. All right. Um, All right, I want you guys to try this one. This is a test they did when they were like right at the beginning of the space race, when they were building rocket engines, designing rocket engines. They would put them on a rail, okay, like on a rail car, and they would fire them, and they would see how fast the thing would go. Okay? There's actually a scene in Indiana Jones in the Kingdom of the Crystal Skull at the beginning where he's on one of these things. Okay, so let's see if you guys can solve that one. There's some acceleration in it before you get to the forces part.
Can I finish?
Yes. All right, so we know the rocket is traveling east on this frictionless rail at a velocity of 11 meters per second. So that's its initial velocity. Okay, then it's going to be accelerated to a final velocity of 22 meters per second in a time of 0.75 seconds. All right, so I should probably find the accelerations. That's usually important in Newton questions, okay, is to know the acceleration. All right, so I'll find that acceleration simply by going VF minus VI over t, so basically 11 over 0.75. Okay, so 14.7 meters per second squared. So about 1.5 g. Okay, so if you were on that rocket, you'd feel 1.5 times heavier than normal due to that acceleration. Okay, so we are looking for the force at which the gases are expelled. Are the gases, the force of the gases being expelled, what's causing the acceleration? Okay, so the force that the gases are expelled at is equal to the force the gases exert on the rail car or whatever it is. Okay, so as long as we understand that, we can calculate the force because it'll be the net force that's acting here. Okay, so we can use the mass of the rocket and this acceleration, and we'll have that force. So we take our 9,800 kilograms times 14.7, and we'll get our 1.4 times 10 to the 5 newtons east. Okay?
Wouldn't it be less because the rocket is going east?
Oh yes, by the rocket. Yeah, it's the force on the, you're absolutely right. That's the force on the gases, so the force on the gases would be west. Absolutely. Good eye, Jonah. Okay. Question on it? Yes. Okay. All right, so with the Newton's third law stuff, guys, just again, on the exam, I usually put like a 2-box question, and not a 3-box question. I usually put a 2-box question on there. Okay, could be frictionless, maybe not. Okay, but we did a bunch like that yesterday. Okay, that's the kind of thing you should expect. So remember that when one box pushes on another, that box pushes back with an equal but opposite force. That's all you have to remember for Newton's third law. The rest of it is Newton's second law. And you guys are good at that. You've done lots of Newton's second law stuff. And the good news is that the Newton's second law stuff in a Newton's third law question is usually pretty straightforward. Okay? There's not like pulleys or vectored forces of any like weird kind or anything like that. It's basically forward and backward because everything is equal and opposite. Okay? Everyone all right with that? All right. So next week here, guys, moving into what we're doing next week. We're going to start work energy theorem on Monday, okay, and we'll probably be looking at the law of conservation of energy by Thursday, and we have one more lab that we'll do that's on conservation of energy, conversion of energy, okay, and then we'll have a unit exam review probably early on the week of the 9th, okay, so like the 6th or the 7th. I guess it'd be the 7th because the 9th is a Wednesday. Okay, and then you'll have your exam, and then we'll go over it on the 10th, and then we'll be into the circular motion unit pretty much right on time because I think I said we usually finish this unit right around Remembrance Day, like 2 days. So okay, we're looking pretty good for where we're at right now in terms of how far we've come. The first 2 units are generally the toughest. Okay, I don't want you to like get cocky or anything, but okay, the next two units typically are a bit easier. They don't involve as much vector related stuff and things like that. Okay, so if you're kind of not happy with where you're at that kind of halfway point, okay, then know that if you continue to work hard, the last couple of units usually bring people's marks up a little bit before the final. Okay, incidentally, on the note of halfway point, you don't have a midterm in physics. Okay, I don't believe in midterms. Okay, other people do. I like to think of them as wrong. Okay, so you don't have to worry about a midterm in physics, just your unit 2 exam, okay, and then moving on from there. Okay, I think I want to make up a question here for you guys to try. It's kind of related because I was looking at your exam and thinking of a good exam question. Calculate the acceleration of the box. Okay, you got a 50 kilogram box. It's being pulled by a 300 Newton force, 25 degrees above the horizontal. Okay, it is going to move along the surface. Okay.
Is it a friction or something?
Mu is 0.250,
Oh,
so
okay.
it's not frictionless. Okay, I'm only going to do a little bit of this in here just because I see a few people that are stuck and I see a few people that have made kind of the most common error that gets made on this, and that's totally fine. That's why I'm doing this. Okay, it's just kind of illustrated. First thing I want to do is, since I have an angled force, but I told you guys it's moving horizontally, is to just calculate the two components of that angled force. The box isn't moving 25 degrees above the horizontal, so there's no sense having the force drawn like that. I might as well just figure out how much of that is horizontal and how much of it is vertical. Okay, so that's just a little bit of trig first. Okay, and I'll want to have my force horizontal and my force vertical. Okay, so to get those, as I said, just a little bit of trig. So cos of 25 times 300 is going to give me 271.89 newtons. And then to get my force vertical, sine of 25 times 300. Okay, so 126.79. All right, we'll look at the rest of that one. That got away from me. Okay, we'll look at the rest of that one on Monday. Have a good weekend, guys, but not too good.
What's the final one?
I don't know. I made it up off the top of my head.